The two pillars of modern physics, quantum field theory and general relativity, seem to be mathematically incompatible. I will not go into details here, as there are so many sources that you can find in the literature or on the internet on that subject. But here is some good news. Not only can we make them compatible, but we can actually derive one from the other, thanks to our new approach to interpret the laws of our universe. Let's see how. The idea here is to show how we can derive the laws of gravitation, and more globally Einstein's general relativity equations, from our new quantum theory interpretation. To do that, we need to see first how to derive the law of gravitation from the structure we have seen in the previous videos, the quantum substratum. We've seen that this playground where mass and energy particles interact is different from the space-time domain where we observe or detect objects and particles. Let's apply these quantum domain rules and other well-known formulas to understand where gravity comes from. First, we'll need to use a concept which has been introduced a long time ago in physics: entropy. A simple example of the entropic state is a sphere containing a few molecules of some gas, say, hydrogen. The relevant state consists in the volume of the sphere, a number of molecules in it, as well as their positions and momenta in that volume. Without any further constraints on the molecules, they are free to access the entire volume, and any position in that volume for each molecule is a legitimate way to create the state we're interested in, namely, 3 molecules in a sphere of volume V. The number of potential positions of the molecules in the sphere can be used to derive that state's entropy. Strictly speaking, thermodynamic entropy S is defined in terms of energy flow at a particular temperature. S equals E over T, but it takes energy transfer in transactions to actualize those possible positions. So the more positions available, the more energy transfer will be undergone by the system. We are going to use entropy to show how a system consisting of a massive object M and a small object M' in the quantum substratum yields the observation of a gravitational force in the space-time domain. I took a few shortcuts to keep things simple here, but you can always refer to the list of publications provided in the video description for more precise explanations. Anyway, the key point to remember from our previous videos is that objects can be detected in 4D spacetime using the energy corresponding to the object's mass to interact with the detector's particles, based on multiple transactions, one of which being stochastically selected and actualized for each detection point. In addition, a principle called the holographic principle tells us that the state of mass m can be described on the surface of the volume including it. So, the sphere surface at distance r from m can be used to represent the positions, among other information, of the components of M. In our example, the change between a macrostate, M plus M prime R, and a macrostate, M plus M prime R plus dx, can be viewed in spacetime as the action of a force which attracts M prime towards M. In reality, it can be interpreted as due to an increase of entropy S as M joins shell R from a small distance dx, and to the average temperature T at R, essentially due to M, because M is much bigger than M prime. That temperature itself is caused by the frequency of interactions between M and M prime. Consequently, the apparent resulting force can be expressed as the product of 2 factors. The first one represents the increase in entropy due to M prime coming from dx, while the second factor is the heat bath temperature due to M. This equation is often used to define what is called an entropic force. Now we can use pretty basic mathematics actually to calculate these 2 factors. So let's do that and see which value we get for the force F. Let's start with the second factor, T of Rm. To calculate the temperature T at a position on R, we can use the E equals 1/2 NkBT formula, where E is the energy of the mass M plus M prime, which can be approximated to M. N is the number of potential transactions with particles at R, which corresponds to the number of possible positions on the sphere surface, and T is the average temperature at each position. We know E, it is equal to mc squared, and Kb, the Boltzmann's constant, so we need to calculate N to get T. For that, we divide the sphere surface by the smallest measurable surface, that is, the Planck surface, Lp squared, as we can neglect curvature, and we get N equals 4 pi r squared over L sub p squared. As L sub p equals the square root of gh bar over c cubed, we finally get n equals 4 pi r squared c cubed over gh bar, and therefore this final equation for the TRM factor. Now we need to take into account the other ingredient, that is, the additional entropy brought in by m prime when it reaches surface r from a previously actualized distance. The actualization of a position at r at temperature T takes an energy, delta E equals 1/2 kBT. So the entropy increase due to m prime reaching r is delta S0 equals delta E over T equals 1/2 kB. But if we assume that the Planck length, LP, is the smallest possible radius in nature, then a single point is replaced by a shell of radius LP around it, and the entropy increase becomes delta S equals 4 pi delta S0 equals 2 pi kB. Also, because there is an uncertainty in a measurement of position equal to what is called the Compton wavelength, lambda c, equals h bar over m prime c, for all distances smaller than lambda c, we get this equation, which yields the gradient ds over dx equals 2 pi k sub b m prime c over h bar. All we have to do now to calculate the entropic force F is to multiply our two ingredients to get this final equation, which represents the well-known force of gravitation as described by Newton more than 300 years ago. So from our new way of describing the quantum world and using entropic and holographic principles, we can derive the classic law of gravitation. And we'll see in the next video how we can also derive Einstein's equations and finally resolve some unanswered problems related to general relativity. So stay tuned!